This video is about the circle theorems needed for Edexcel Maths GCSE, but they'll be the same for every exam board, so it doesn't really matter what exam board you're on. Theorems don't change, hopefully. We're going to start with some basics, so I'll go as quickly as possible because it's really boring, and if you already know it then I'd just skip a few minutes to avoid this because it's really easy stuff. So it's just definitions mainly. So a chord is a straight line joining 2 points on the circumference of a circle, like that lovely red line there. And segments are the two parts of the circle that are on either side of the chord. And there are two segments in the diagram. The arc is the part of the circumference that joins 2 points in a circle, circumference. That was nice repetition there. And it's that green bit, so it's the lovely curved bit there. I keep describing everything as lovely, it's like my word of the day. A cyclic quadrilateral is a four-sided shape whose vertices, or corners, all lie on the circumference like that red shape. A radius is a line coming from the centre of a circle to the circumference, and when it touches a tangent, you'll get a right angle, like that green right angle there, because you can always have a radius at any different angle, so you can get it so it'll be a right angle, and the one that touches the tangent will be a right angle, in case I didn't make the right angle thing too obvious there. The length of any two tangents from a point to the circumference of the circle will always be equal. A radius that's perpendicular to a chord will always bisect the chord, which means it will cut it in half. That's the end of the easy part, unfortunately, so we've moved on to the theorems, and I'm probably not that good at explaining them, but I couldn't log into my Maths because I've forgotten the password, so I had to do this instead. The first theorem is that the angle at the centre of the circle, which is the purple bit, is always twice the angle at the circumference from the same arc, and that's the red bit. I didn't want to write that out every time, so I've just shortened it a bit, but maybe I should have shortened it and made it in bold or something. You can't really tell it's a title, but it doesn't really matter. So to start your proof of this, you have to draw in an extended diameter which splits the circle in half, and you should now have two isosceles triangles, so AOP and BOP. BOP, BOP to the top. Isosceles triangles are triangles that have got two sides and two angles that are equal. So if we look, we can see which two angles are equal, so we can say that OAP is equal to A, and OPA must also equal A because the two angles have to be equal, and there are 180 degrees in a triangle, so AOP, which is the big angle, has to be 180 minus 2A. We know that angles in a straight line add up to 180 degrees, and we know that that blue line PD is a diameter, which is a straight line, so we know that the angle DP, if that's the name of the angle, I don't know what you call that angle, but that angle has to be 180 degrees, and we know that the angle AOP is 180 minus 2A, so we can therefore infer that angle AOD is 2A. So we know that on the left hand side of the diameter we've got the red bit, which is A, and the purple bit, which is 2A, which is obviously double A. If we do exactly the same on the other side, we can use triangle BOP to prove that DOB is equal to 2B, so using all the orange stuff to work out that angle BOD or DOB is equal to 2B. So we know that AOB, the big bit, equals 2A plus 2B, which is the same as 2A plus B, and the angle at the top, the red angle, APB, equals A plus B. So we know that angle AOB is double angle APB. So that's the first proof, which is the most important proof, and we use it in basically every other proof. It's that important. So you have to know that proof. So sorry if I haven't explained it well enough. So we're moving on to another theorem, which is basically an application of the previous theorem, proving that angles from the same arc in the same segment are equal. If you look at the diagram, you can see that we've got a few other angles that are in the same arc and the same segment, and that they're equal. Because if we use the previous theorem that angles at the centre of the circle are always double the angle at the circumference, we can see that they share a common centre angle. So we know that AOB is 2 times APB, and because it's the same for all of them, it's got to be 2 times ALB and also 2 times AGB, so we know that APB must equal ALB, which must equal AGB. Hopefully that made sense to you. If not, I'd go watch the previous theorem again. The next theorem is that the angle in a semicircle is always a right angle. I'm trying to sound enthusiastic here, but me, maths and enthusiasm are not words that I tend to use in combination. Anyway, back to proof. We can use the first theorem, which is that angles at the centre of the circle are always double the angle at the circumference, to prove that angles in a semicircle, so basically if we have a line in the middle, the angle, any angle within that semicircle, will be a right angle, because we know we've got our diameter in the middle, which is a flat line, and angles in a flat line, so AOC, are always 180 degrees. So we know that ABC is half of angle AOC, so it must be 180 divided by 2, which is 90 degrees, which is a right angle. We're on the next theorem now, which is that opposite angles of a cyclic quadrilateral add to 180 degrees. So we're basically saying that angle F and angle G add to 180 degrees. Casually hissing at the microphone there. So we've got our original diagram that you saw on the previous page, but we've added some radii. I looked this up. You can either call it radii, or however you pronounce it, or radiuses, but radiuses sounds really weird, so I went for radii. And we can use the first theorem, again, to prove, because we know that angles at the centre of the circle are always double the angle at the circumference, we know that BOD, the obtuse one, is 2F, and because it's double F, which is BAD, bad, haha, and I get entertained by small things like that. And we know that BOD, the reflex angle, must be 2G because it's double G, which is angle BCD. The angles 2G and 2F are on a point, and we know that angles that are at a point add to 360 degrees, so therefore we must be able to infer that 2G plus 2F adds up to 360 degrees. But obviously we only want F and G, because at either end of the cyclic quadrilateral we've only got F and G, so we divide it by 2, and 360 divided by 2 is 180, so we know that F plus G, which are opposite angles of a cyclic quadrilateral, add to 180 degrees. Yay! Not gonna lie, learning about circles is pretty pointless. Ha ha ha! I found that funnier than I ought to have found it. Okay, now we've got the horrible last theorem, which is that the angle formed between a tangent and a chord is equal to the angle from that chord in the alternate segment of the circle, otherwise known as alternate segment theorem, which is much shorter and easier to remember. And we're basically proving that the green angle is equal to the blue angle. You'll know it'll be alternate segment theorem because you'll have an annoying angle bit that is like just in the middle of nowhere, and that's the blue one called theta, which is that random symbol. And you'll be told to find angle Z, which is the green one, when you've been given angle theta. And the triangle you'll start with is triangle PSY, who also happens to be a Korean rapper. But you've got to add another triangle in. So you add in triangle NSY. So NS is the diameter, SY is the chord to point Y, and then you just add another point chord from N to Y. Now we're going to use the first theorem again, and that proves that angles at the centre of the circle are always double the angle at circumference, so we know that angle NSY must be 90 degrees, a right angle, because NOS, which is the diameter, is 180 degrees, and 180 degrees divided by 2 is 90. We know that the angle between a tangent, which is the black line at the bottom, and a radius, which is the diameter essentially in this case I guess, OS, is a right angle. So we know that angle NSY must be 90 degrees, but we know part of it's theta, so it must be 90 minus theta. We're still working on the pink triangle here, and we know that angles in a triangle add to 180 degrees. So SNY plus 90 degrees, which is the right angle from NYS, plus 90 minus theta, which is what we worked out NSY to be, must equal 180 degrees. So we know that SNY equals 180 minus 180 plus theta, which equals theta. We got the 180 from the 90 plus the 90, and then we took the 180 from that side and added theta to that side. So we know that SNY is equal to theta. We know that angles in the same arc in the same segment are equal, so we know that angle SPY is equal to angle SNY, and we know that angle SNY is theta from all the proof we did earlier, so therefore we know that SPY must therefore equal theta as well, so we know that the green angle is equal to theta, which is the blue angle, yeah! Woo, that's the end of circle theorems, yeah! Sorry my explanations haven't been very good. If you don't understand it, just go back and go at your own pace without my annoying voice in the background, or go on My Maths or something like that. Yeah, so sorry if I was going off on a bit of a tangent there. There's no end to the number of jokes you can make about circles. Woohoo!